Hey guys, in this video I'm going to be going over counting change. This is a very popular interview problem and a classic DP problem. So counting change is a problem where given a instruction like change, an amount, and an array of coins, you want to return an integer which is the minimum number of coins to get this amount. So what does this look like? A typical input would look something like 100, 1, 5, 10, 25, which accounts for pennies, nickels, dimes, and quarters. So how do we visualize this problem? Given an input something like 10, we can start visualizing this as a tree. The answer to do this is a recursive problem. So we would go through the amount and attempt to subtract the coins in the coin array from the total and recursively call the function. So we would call change 10, 1, 5, 10, 25. And then in the recursive function, we would call it first on 1, reduce it to 9, which in turn would reduce it to 8, reduce it to 7, 6, 5, 4, 3, 2, 1, and then 0. So our base case is if amount is less than or equal to 0, then return 0. Next, once we hit 0, we're going to be returning the amount, 0. 1, we can't use 5 and 10, so we would be returning 1. Here we can't use 5 or 10, so we'd be returning 1. Can't use 5 or 10, we'd be returning 1. Can't use 5 or 10, so we'd be returning 1. And at this point, we would have added up these coins, and this would be a 5 for 4 for pennies. So, 5 pennies. Now, at 5, we could also use a 5 and go straight to 0. This would return 1, and 1 is less than 5. So therefore, the minimum number of coins to make change for 5 is 1. We would repeat this for all these different values. So 6 can be reduced by 5, which in turn 1, and then this would be 0. So the minimum number is 2, 7, 5, 2, and then 1, 0. So this would be 3, 5, 2, 1, 0, which would be 4, 9, which goes down to 4, 2, 1, 0, which would be 5, and then 10, which goes down to 5, which can go down to 0 through a series of 5 pennies, or go down to 0 with 1 nickel, and then 10 can also go down to 0 with 1. So the minimum number would be 1. Cool. So this is sort of the recursive function and the logic behind it. So to execute that logic, we would have to have a a value to hold it, which could be best try. We set that to a sentinel -1 for now. And then we would have to iterate through each coin in the coin array. And we would have to check if the coin is less than or equal to the current amount. This makes sure that this operation is possible, and we would call next try is equal to the recursive call of change minus the amount minus the coin. And we would pass in the coin array with that. This would call the recursive function to go down the tree until we hit a base case, which is amount is equal to 0. Now, try best try. If best try is equal to -1, which meant that it hasn't been set yet, or the best try is greater than the next try, then we set best try is equal to next try. So I want to take a second and look at this logic. This basically will make sure best try is always set. And then the second piece of logic, best try is greater than next try. This is to make sure that we're always getting the minimum number. So if the current best is greater than what it would have been in the recursive call, then we set best try to the minimum amount. And now we can, when we're done with this loop, that means we're done with the recursive call, and we can return the best try. And remember, in this recursive call, as we go deeper in the recursion, we're always going to be bubbling up the minimum number at the end of every recursion. So by that logic, once we reach the end of the recursion, this will be the minimum amount of change minimum number of coins to make change. Cool. So that is the brute force solution, and the runtime would be O of 4n in this case, because we're going to be recursively calling every sub-array with every coin value. Now, we could actually speed this up, because since we're going depth first in this tree, when we get to the bottom, we actually calculate the value. So if we ever get to that point again, then we can just refer to that value if it was stored in some sort of array, like a memo, like a list. So we're going to be using this process called memoization. And how we're going to be doing this is we're going to be saving the value at every amount with the minimum number of coins to make that change. So at amount 0, it would be whatever that is. At amount 1, it'd be 1. At 0, it'd be 0. At 2, it'd be 1. At 3, it would be 1. or at 2 would be 2, at 3 would be 3, at 4 would be 4, at 5 it would be 5 or 1. It would take the minimum and keep that. So now when we're at 6, we go to 5, and we already know that the minimum amount is 1. So we can not look down the recursion anymore and take this value and build on it by adding a penny, and now we are at 2. So to visualize that in a tree, that basically means that when we go down and we hit a node that we've already explored, then we cannot keep on searching and just take the value that we already computed and just pass that up the tree. So how do we write that? We use change, and we're going to be creating a new variable, a new argument. We're going to be taking the amount, we're going to be taking the array, and we're going to be taking a memo. The memo is going to be a list filled with -1 for now. And we're going to be checking the base case. We're going to be returning 0. This doesn't change. But what we do here before we even start the recursion is if the memo amount is greater than -1, then we just return the memo amount, and we don't even go down the recursion. Other than that, the recursion would be the same. And at the end, we would store the best try in the memo. So now what this execution does for a value like 10, it would go down and then when it hits 0, it'll take 1 because it already knows it's 1. 0, and then 1 would take 1, 2 would take 2, 3 take 3, 4 take 4, 5 would take 1. Now 6 would go to 5, it would take 1, and then add 1 to it because we added a penny. Now 7 will go to 6, we'll take 2, and then add a penny. 8 will go down to 7, it'll see 3, and then add a penny. 9 will go down to 8, it'll see 4, and then add a penny. 10 will go down to 9, it'll see 5, but 10 will also go down to 5, and it'll see 1. But also 10 can also go down to 0 by adding a dime. So then 10 will keep 1, and then we're done with our recursion. So to call this function, we would do something like this. And this is to make sure that we have an array of length 11 because we want to hold 10 values inside. So there we go. That's counting change. Which both the brute force and the memoized version.